Okay, so I'll talk about the exponential type conjecture in quantum connection. So let me maybe explain the setup. So let X omega be a closed monotone symplectic manifold. Um, and on such a manifold, genus zero Gromov-Witten invariants give rise to a multiplicative structure on the singular cohomology of X, which is called quantum cohomology. So for instance, if you have two cycles alpha and beta, then their quantum multiplication paired with another class gamma is given by the count of these kind of three-pointed Gromov-Witten invariants. Okay, so hopefully this is familiar. So the quantum connection is built out of three-point genus zero Gromov-Witten invariants in a very elementary way. So this version of quantum connection I'll use is the quantum T connection. It's a connection on the singular cohomology of X with, for now, just an arbitrary coefficient ring adjoining a formal variable T. It's given by this formula. So it's d over dt plus quantum multiplication by the first Chen class over t squared plus mu over t. So where this mu is some grading operator. So mu restricted to the degree q cohomology class. It's given by multiplication by q minus the complex dimension of x over 2. So this is a connection with a quadratic singularity at t equals 0 and a regular singularity at t equals infinity. So if you make a change of variable t equals, say, 1 over q, then you'll find that at q equals 0, it will only have a simple pole. So this regular singularity is somehow well understood. There is a fundamental solution which has interpretation for in terms of generating function for Gromov-Witten invariants. And this quadratic singularity is sort of mysterious. In general, we don't have a good classification of solutions to a quadratic singular differential equation. So maybe a first step in understanding this quantum differential equation at t equals 0 is to ask, can we say more about this singularity type at t equals 0 instead of just being a generic quadratic singularity? And this, an expectation for this is formulated in the conjecture of Kutarkov, Kontsevich, Pentiv, and separately in Galkin, Gerlach, Iritani. So the statement is the following. So over the complex numbers, so there exists a finite decomposition of the connection, the quantum T connection, where for each component of the connection has the following form. It is gauge equivalent to a one-dimensional connection, d over dt minus lambda over t squared, tensor with another connection, which is regular singular. Okay, so maybe I should give the definition. So regular singular just means it has a simple pole after a potential gauge transformation. Okay, so, and this kind of decomposition is called the exponential type. It's unique if it exists. Hence, this conjecture is something also called the exponential type conjecture. So we can think of this as some kind of spectral decomposition of the connection, if you like. So the main theorem I want to talk about today is that this conjecture is true for all closed monotone symplectic manifold X. So before I talk about the proof, I want to make two remarks. So first, why do we care about this exponential type property being true? So in some sense, these are the simplest irregular singularities. So in particular, one can study their fundamental solutions by a Fourier Laplace transform. And the important property of those kind of exponential type singularity is that their Fourier Laplace transform are regular singular. So we can study their fundamental solution and associated Stokes phenomenon. And those are underlies the very famous gamma conjectures. And the second remark is before my work, there's this work in a series 2 papers by Pomigliano Seidel. They prove this conjecture when X has a smooth symplectic divisor who's complemented to Einstein. And their assumption is basically because they have to pass through this complement and use some information about the Foucault category. While my proof is essentially closed string. Okay, so now let me start the proof. So the strategy of proof is to use mod p reduction, and I'll roughly sketch 3 steps. Okay, so the first step is mod p reduction and Katz's criterion. So in step 1, so this is an elementary fact, which one can prove just using solving for power series solutions step by step. So there exists a domain R, which is finally generated over the integers, and such that the fraction field is characterized to 0. Such a ring is called a global ring. And over such a ring, there exists a unique decomposition labeled by the eigenvalues of C1 star of the connection. So with the following 2 requirements, first of all, this decomposition is preserved by the quantum T connection. And the second requirement is that if you restrict this decomposition to T equals 0, then it is equal to the generalized lambda eigenspace of C1 star. And these 2 requirements uniquely determine this decomposition. So a consequence of this decomposition is that for each piece of the connection restricted to, well, for the connection restricted to each piece of decomposition has a very simple form. So it is equal to d over dt plus a quadratic term, which is lambda plus n lambda. So this is like a Jordan decomposition of the C1 star, plus another term gt, which has at most a simple pole. So let me circle this part out. Okay. So this part, so we remove the lambda from this connection form, and I'll call this part the residual connection, lambda tilde, or nabla tilde. So the original statement requires we show that this nabla tilde QH lambda is regular singular. And for this, we use Katz's criterion, which says if we reduce mod p, something happens, then this connection is regular singular. And what exactly is this criterion? So if we have a connection on a variety over a global ring, Katz's criterion says if for almost all maximum ideal of R, the reduction mod this ideal has nilpotent p curvature, then the original connection, base change to the complex number, has regular singularity. So what is p curvature? So if you have a connection on a variety in characteristic p and a vector field, then the p curvature of nabla along D is given by the following formula. It's given by the difference between the pth power of the covariant derivative with the covariant derivative with the pth power of the vector field. And here we're using the crucial fact in the characteristic p. The pth iteration of a derivation is still a derivation. Okay, so this expression makes sense. So by Katz's criterion, it's immediate that if we want to show that the original connection, this tilde nabla is regular singular, it suffices to show that the p curvature is nilpotent. And we observe that the p curvature of this nabla tilde is equal to the p curvature of this original nabla minus lambda to the pth power over t to the 2p. Okay, so that's just a very simple computation. And to show that this p curvature is nilpotent is where this new operation, so this quantum string operation comes in. So this is also a topic of a talk of J.H. Lee here about a month ago. Here I'll just do a very brief review of what these operations are. Okay. So these operations are generally due to Fukaya and studied intensively by Nick Wilkins, is a series of operations of quantum cohomology in a field of characteristic P on singular cohomology adjoining this formal variable T. And to be completely precise, sometimes there's this formal variable theta involved, but for now I just ignore them. So how is this operation defined? So if you have a class, say a class beta, class B in quantum cohomology, and a Carrerian class alpha, then the operation So the operation Q sigma B of alpha is defined by counting the following kind of genus zero invariant. So you have the domain is another copy of CP1, but now there are P plus 2 mark points. So one mark point is input alpha at 0 and another output at infinity. And then the remaining P inputs are at the roots of unities along the equator, and they're all incident to this cycle B. And moreover, we count them Z mod P covariantly, where the Z mod P action rotates the domain along the equator. Okay, so I won't precisely define what counting Z mod P covariantly mean, but it's some kind of Borel construction and using Z mod P covariant perturbation data. Okay, this Q sigma is called the quantum Steenrod operation or the quantum Steenrod action. So the final step in the proof results in two ingredients. So the first ingredient, which J.H. Lee talked about a month ago, is that quantum Steenrod operations are expected to be related to the P curvature of the quantum connection. So he formulated and proved a precise version of this statement for symplectic resolutions. So for us, in the monotone case, the statement is due to Seidel, and its precise statement is that the quantum Steenrod operation restricted to the first Chern class is equal to the P curvature of the quantum connection along the vector field T squared d over dt. And this statement ultimately is a corollary of a statement of Seidel-Wilkins, which says that the quantum Steenrod operations is covariantly constant with respect to the quantum connection. And the second ingredient is a technical lemma, which says quantum Steenrod operations are compatible with the decomposition, which I mentioned above. And 1 plus 2 gives the desired nilpotent result, which by Katz's criterion gives the desired regular singularity or the exponential type property for the quantum connection. Okay, so here's this. So I finished the scheduled proof. Maybe I should pause to see if there are any questions. Okay, so if not, I will talk about the last section. So the last section is that all of the above should admit vast generalizations to the case of non-commutative geometry. And roughly speaking, what do I mean? So for instance, the quantum cohomology of a symplectic manifold X should be recoverable from the Hausdorff cohomology of its Foucault category. And this is a very classical result due to a bunch of people, Seidel, Foucault, Ono, Ganatra, Richard Smith in different settings. And slightly more refined is the statement that this equivariant singular cohomology with the quantum connection should be recovered from the periodic Hausdorff homology, or sorry, the periodic cyclic homology of the Foucault category together with its Geisler-Gauss-Mannich connection. This were conjectured by Ganatra, Perutz, Sheridan, and proven in various cases by Huxenbud and Palmiano Seidel. And because further, if we work over a field of characteristic P, then the quantum Steenrod operation is recovered from an operation of Hausdorff homology on periodic cyclic homology called the Z mod P equivariant cap product. So this is proof in one of my papers last year. And finally, I have a work in progress which aims to prove the analog of Seidel-Wilkins statement that quantum Steenrod operation is covariant constant. So this analogous statement is stating that the Z mod P covariant cap product is covariantly constant with respect to the Geisler-Gauss-Mannich connection. So, okay, so maybe I can talk a little bit about what this Z mod P covariant cap product is. So there's a formalism of Kontsevich-Soberman, which assigns an operation of some copies of Hausdorff homology acting on Hausdorff homology. Really is a chain level action. But let me just abuse notation and say H is upper star and H is lower star. So these operations are somehow labeled an operator which consists of configurations on a cylinder. So you can have a tree that looks like this on a cylinder. And this will give us an operation of Hauser cohomology and Hauser homology where this copy n is equal to the number of circles on the cylinder. And this Z-multi covariant cap product arises from a particular kind of configuration of forest. It looks like the following. So we start with a very simple tree. So if we give it this should correspond to the usual cap product. But now I can consider the Z-multi orbit of this single tree along the Z-multi action. So this has a Z-multi symmetry. And if we take the Z-multi fixed point of this action, this will exactly be the Z-multi equivariant cap product, which I just mentioned. Okay, so given this generalization to non-continuity geometry, there are some further questions we can ask. So the first question is, does the analog of J.H.Lee's conjecture hold in this case? Or that is, what is the relation between the Z-multi equivariant cap product with the p curvature of the Gessler-Gauss-Mann connection? And the second question, for instance, is another conjecture of Kontsevich-Pentiv, which says that for general Z-multi graded uncurved A infinity category A, the Gessler-Gauss-Mann connection should be expected to be regular singular. And given this approach to the exponential type conjecture, one can ask, can we use reduction mod P to prove this conjecture as well? And unfortunately, it's not so easy. There are some issues presented for a general category, which is not present for a symplectic, a monotone simply manifold, such as the Hodge to de Rham degeneration. And second, there's no analog of the Novikov variable for general A infinity category A. And another interesting question, which is still widely open, is if A is derived category coherent sheaf on the variety X, what does this Z-multi covariant cap product cover? So this should be some operation on differential forms, on vector fields on differential forms in characteristic P. And there are some conjectural answers and a few examples, but the general picture is still very unclear. So so that's the end of my talk, and thank you very much for listening.
Thank you. Any questions?
So I want to add, oh, sorry, go ahead.
Sorry. Can you give a little bit of context on where this connection come from and why you study it? And
yes, so where does connection come from? Yeah, so I guess this quantum connection has a lot of different forms. So the one people study is the one which is regular singular and zero, okay, called the Q connection. So this looks like d over dq, sorry, q d over dq plus 1 over t c1 star. So this connection, so its fundamental solution say q equals 0. So this corresponds to a generative function for genus 0 when we went to the variance. So first upshot is that if you understand this connection very well, you understand this genus 0 Gromov-Witten variance very well. And the second interesting thing about this connection is that so at q equals infinity, which is roughly speaking this T connection, which I talked about in my talk. So one can sort of analytically continue these fundamental solutions. it's the reverse. So if we study the fundamental solution at q equals infinity and analysis continue towards 0, then this will give rise to cohomology classes. And there are very precise conjectures about where these cohomology classes should correspond to. And these are formulated in terms of the gamma conjecture and also, say, Dubrovin's conjecture. Important, I guess, questions in the field of Gromov-Witten theory. And they sort of explores, or they sort of formulated unexpected relations between K-theory classes and solutions to this quantum connection. So these are questions which are sort of, to understand this gamma conjecture, you have to first, say, prove the exponential type conjecture for a general Fano manifold.
Thank you.
Yeah, so I want to advertise that right after this talk at 10:45, there's a talk by Paul Seidel at the Miami Homological Mirror Symmetry Conference, which is available on Zoom on very related topic of quantum connection, and it's a full-hour talk. So if you are interested, you should check it out.
Okay, so thank you, Chang, and